Hi, my name is Omana Chloe Amunjaza, and I'll be talking about my project, Quantum Phase Detection using AI. So in general, the challenge that we're trying to solve here is trying to have a model that's able to identify thermodynamic states and the temperature that caused a snapshot to be in that state based on the Ising model. So the Ising model is essentially a grid where every pixel represents the spin state of an electron. You can think of the like grid as a toy magnet or a snapshot of a slice of a magnet. So essentially, the idea is each pixel here represents a spin up or spin down. So the Ising model is technically used to simulate magnetism, where an ordered phase is seen to be magnetic and is usually associated with lower temperature, and the spins tend to be aligned. So in this case, as you see, this is an ordered phase, and you see that your clusters of spins, they're about the same. Your clusters of like particles are about the same spin. A disordered state is at a point where the metal is seen to be not magnetic. And this is usually associated with higher temperatures because heat adds energy to the system and increases like the probability that spins will flip and neighbors will become like unaligned. So the important thing here is the critical temperature, which is essentially the temperature at which a certain metal loses its magnetism, and it marks the point as that we move from an ordered phase to a disordered phase. For this project, I'm using the base value of 2.269 units of temperature, not necessarily any degree, but we can just understand it as a base unit of temperature. So the goal here is if we can get a model to look at this grid and identify that this is an ordered phase for the classification task, and then for the regression task, identify if the temperature, if we can find out what the temperature is based on the snapshot. So this is the information that the model is given, and this is the information that we want the model to return, the state and the temperature. All right, so for the data and architecture, for data generation, I generated a 16 by 16 grid using the Metropolis Hastings algorithm, which is just a form of Monte Carlo, like data generation. So we generate random values for a 16 by 16 grid, and then we for each grid on for each spin on the grid. So for each item in the grid, we calculate the change in energy if that spin were to be flipped. Now the change in energy depends on its neighbors. So like the up, down, left, right spin neighbors. And the spin like wraps around. So we also kind of account for that by using like modulo in the code as you might see. So if there is a change in energy that reduces the total energy, we accept that spin. If that just means that the neighbors are probably around the same as the spin. So if flipping the spin would cause us to align with our neighbors, we basically want to always accept that. However, if flipping the spin would cause an increase in the energy in the system, we want to probabilistically accept that based on like this equation, which is strongly driven by the temperature of the system, which basically tries to simulate what actually happens in real life, where like increased inject like temperature or energy based on like thermal energy being injected into the system, like determines probabilistically determines if like a spin can flip up or down. Now, the models that we're trying to use here are about three of them for the project. The first is the baseline model, which is basically my logistic regression model. This is just a linear classifier. It's not expected to do great. It ended up doing really like, kind of well, but we'll get into that later. It's not expected to do great. It's just supposed to at least set a baseline for the other models to do better. So I flattened the 16 by 16 grid to a vector of size 256 and passed that into the logistic regression model. The next is the MLP model, which is multi-layer perceptron. It's not linear, but it still uses the flattened inputs, and this basically causes it to discard spatial information. So this was expected to do better than the baseline model, but it still wasn't like perfect. So after talking to my TA, we decided to add a CNN to the project. We didn't really cover this in class, but like it was around Thanksgiving, and I figured it'd be something like interesting to, or it was a bit before, and I figured it'd be something interesting to add in to see how well it did, since now we're preserving the spatial information. And these were the results. As we can see here, I essentially used two main data sets. A data set that included temperatures at extremes, so really low temperatures and really high temperatures. And we see that most of the models did really well here. Next is the critical temperature. Now, the logistic regression model didn't do too great here, which was kind of expected, because now at a critical temperature, the snapshot won't look very clear. It won't be as organized as this, and it won't be extremely disorganized like this. So we expected it to not, we expected the models to like fare worse here, and they did, but the CNN classifier still did better, which makes sense because it is the only model that actually preserves spatial information. Next is with the regression performance. So this is kind of based on the temperature. We want to see how far off the model is um, temperature-wise. So we saw that we basically used two metrics here. For classification, we used accuracy, but for regression, we kind of wanted to see like how far off we were. So we used the mean absolute error. So we noticed that with the MLP, at least I noticed that with the MLP regressor, that it was about 0.248. It kind of varies depending on when I ran it, but it basically was in that range of 0.248 to 0.3, off from the actual. And then the CNN regressor actually did a lot better. It usually stayed below 0.2. In this case, it was 0.177. I also just showed some data here for root mean square, but you're basically telling the same story. That's the CNN regressor just always does better. So that's like the kind of main results that I noticed here. I'm really glad that I added the CNN piece to the project because it's very interesting to see how much better it actually does to the other models, now that it's given the information. It is also interesting to see that the other models actually did well at all, especially the logistic regression model that just uses like linear, like just uses a linear approach. But yes. This is a very interesting project, and I'm really glad I got the chance to like practice some of this with a field that I'm really interested in. Thank you.